There's a problem on CO2, and it says if the translational root mean square speed of the water vapor molecules H2O in air 648 meters per second, what is the translational RMS speed of the carbon dioxide molecule CO2 in the same air? Both gases are at the same temperature. By the way, if they were not at the same temperature, what would happen in a gas in gas mixture is that some of them would be actually too fast, would bump into the others, would speed those up, and therefore become slower, so give off some energy, and the overall outcome is that the temperature equals out to be the same among all the gas molecules. That means the root mean squared speed, and therefore the average energy, and therefore the average temperature being all the same for all of the gas molecules, respectively gases, in a mixture. That's why they say the temperature is the same for both CO2 and H2O. Okay, let's see what they have given. They have given the VRMS for H2O, but they want to figure out what it is for CO2, and basically that's it. Then of course they say that the temperature is the same for those, and let's see what we're going to figure out here. Well, this is under the header of the kinetic theory of gases, so we look in there what kind of equations we have, and one of them says that the average kinetic energy is 1/2 mv squared. So it sounds like that it's basically the only equation that one appears, VRMS squared, and that equals, and so we have 3/2 the Stefan Boltzmann constant K times the temperature. And this is the way we should do it for the H2O. Just going to copy this here. I think I need it in just a moment. So for the H2O, we have this one here given as 648 meters per second. The mass of the H2O, well, we just looked that up. It's in the front of the book. What the mass of a neutron or proton is, and multiply that with the number of nucleons that we have. And in H2O there would be 18 of them, one each for the H and 16 for the O. So we figure out what the mass is, therefore then we figure out what the temperature is, and then we use the same equation and plug that in then for the CO2. So now we would know what the temperature is and plug it in here, and we know what the mass is for the CO2, where on the CO2 we would have a mass of 44 times the nucleonic mass, because this one each is 16. 2 times 16 is 32, plus the 12 here is 44. Okay. Anyway, actually I'm going to do the problem here. Just going to need perhaps a little bit more space. And I set the 2 equal on the right hand side because it says it's the same temperature, and therefore I'm going to come up with m VRMS squared for the H2O equals m VRMS squared, with very bad handwriting, for the CO2. And as I said, the right hand side equals, of course nothing survives there, and then of course both have a factor of 1/2 which divides, and then I figure out what the VRMS is of the oxygen, I'm sorry, of the CO2. So for the CO2, by dividing by the mass of the CO2 on the other side, so I have the ratio of the masses. So m of the H2O divided by m of the CO2 times VRMS squared. And if you imagine that there's a square here and that there's a square here, and I need to get rid of that square here, I take the square root of the right hand side, which gets rid of the square here, but it introduces a square root right there. Again, I trust that you need to know the algebra on this one here. And then when I plug these in, all I actually need to do is take the 18 that I mentioned earlier, divide by the 44, take the square root, and multiply by the, what was that, 648 meters per second, and I come up with the RMS speed for CO2, which will be less because that fraction here is less than 1, and that makes sense. The CO2 is more massive, and therefore in order to have the same energy, this is what it says here, with the right hand side being the same, the left hand side, the average energy is also the same. So for a molecule that has more mass, the CO2 44 versus 32, it has to have a smaller speed. And then I actually don't need the nucleonic mass because that would divide out anyway once I plug it in here. So all I have to do is the square root of 18 divided by 44, and then I multiply that with the 648, and I come up with an average speed of 414 meters per second. By the way, again, where I came up with the mass numbers is actually on the beginning of the book, it's the back of the book, table of the elements. You look at the mass numbers for, or atomic numbers for oxygen, and which is, I'm sorry, not atomic numbers. Atomic mass was correct. So you look it up for oxygen, which is virtually 16. You look it up for carbon, which is virtually 12. You look it up for hydrogen, which is virtually 1. Even rounded to 2 or 3 significant figures, and yeah, the answer then is 414 meters per second. The reason I put the Earth here is because we have a very thin layer of the atmosphere, and what holds the atmosphere to the Earth is Earth's gravitational force, so that holds it on here. But of course we know that rockets can leave the Earth if they attain a certain amount of speed, and molecules can do the same thing. So if molecules are fast enough, they can actually leave Earth. They can leave the Earth, and that is called the escape velocity. And that escape velocity for Earth, that can be calculated from an equation that may or may not be in our book in some other place, and comes out to about 11,000 meters per second. Now look at this result here, 414 meters per second for CO2 and 648 meters per second for the H2O, and we can see that's quite a bit smaller than the escape velocity, and so we're able to retain CO2 and H2O. Of course, that's a root mean square velocity, which is kind of an average velocity, but there are velocities, some molecules that are much faster than that, and that goes with the curve that you find in the Maxwell distribution. So some of them, but very few, may leave Earth's atmosphere. However, if you compare that to H2 molecules, so just hydrogen gas has an atomic mass of 2 compared to the CO2 of 44, so the ratio there is 22, and this of course here implies the square root of that, which means that the root mean square velocity speed of hydrogen is approximately 5 times higher than that, so you come up with 2,000, and that 2,000 meters per second for the root mean square velocity of hydrogen in hydrogen molecules in our atmosphere is large enough that in the past there were enough molecules at a faster speed that they actually escaped Earth, and then give it enough time, actually all of them pretty much escaped. And that's why we don't find light gases like hydrogen and helium in our own atmosphere, because with their little mass, their root mean square velocity was just too large, and they were able to escape Earth.